Hi, let's talk about signals today. So we're looking at wireless hacking, and we really want to get hands-on with Aircrack and John the Ripper. We want to be able to pivot throughout networks, connecting to wireless access points to then go on to an enterprise or go on to cloud architecture. But in order to do that, we have to start at ground zero. So we have to start with the signals, we have to start with something called the electronic magnetic spectrum, which will be referred to as EMS. And in order to start, the military's been doing this for about longer than 80 years. Probably in the early 1900s, it really started picking up. But one could even argue that it started back with Tesla. So before we continue going down our hands on the keyboard wireless hacking techniques and creating some tools, let's talk about radar, which when you're talking about EMS, radar covers a whole spectrum and multiple bands within the EMS or electronic magnetic spectrum. The ones that we're concerned about for the EC Council's upcoming class, wireless hacking class, is going to be mainly in the 2 to 5 gigahertz range. So we'll talk about what a hertz is, the unit of hertz. We'll talk about what common nomenclature we normally associate with different technology frequencies. And we'll touch upon how it looks on the physical medium, so layer 1 of the OSI model. But in this scenario, 2.4 to 5 gigahertz is the common household frequency range for your wireless router for different networking technologies. Now, with the Magma project coming up for Facebook and the Linux Foundation organization, there is starting to be a blend of frequency bands that's commonly associated with Wi-Fi and with cellular devices. So in 2019, there was an Android app that helped fuse LTE and Wi-Fi together to provide faster Wi-Fi for your devices or for your Android phone. And what that means is, even though we're considering the 2.4 to 5 gigahertz range for networking devices, that may not be the case in the future, especially with 5G. So 5G, from my understanding and from what I've looked at before, really touches upon anything past 30 gigahertz. When a few companies were first starting in 2019, they were looking at the 60 to 64 gigahertz range, and it just depends on the time of the day, the weather, depending on whether it's raining or not, because you have different water absorption that affects higher frequency waveforms. And going further, we'll talk about these over the next 120 days or so. But let's start with radar, and let's talk about SIGINT principles associated with just traditional radar. So on the left, I wanted to start applying this towards networking, infrastructure, and technologies. So this looks like a parabolic dish, or at least it should. And what it does is it can first assume this is the hacker. Let's talk about it from the hacker's perspective. Assume that this is transmitting a pulse. So later on we'll talk about how you encode different data within waveforms and what your encoding scheme is going to be associated with layer 1 or the physical medium. But in this scenario, we'll just say it's transmitting a pulse. That pulse is propagating through free space, and it's hitting our target. Just wanted to draw a generic symbol showing, different, receivers in this case. And what's happening is when you're talking about Cisco gear, especially when you're talking about the cloud and you're talking about smart city technologies, they're posting different patch antennas throughout cities on different telephone posts and on different parts of whatever architecture you're looking at for that particular, I guess, pod deployment. And so what I'm saying is we're trying to target an endpoint associated with the Merkle cloud or Cisco's cloud architecture. And so in order to do that, we have to use a parabolic dish or an antenna. It doesn't have to be a parabolic dish that transmits electronic waveforms to its target and essentially gets an echo or reflected signal coming off of that. And what that's doing in the radar world, that's called the target cross section, or the RCS, which is radar cross section. In this scenario, we're not as concerned since a lot of those patch antennas or pod deployments are not actually moving. But when you're talking about smart cities, you could actually have different network services that are mobile. So going forward towards 5G and next generation cellular communications, you might actually have to be concerned with RCS. Just want to throw it out there. So what is this traditional radar? So when we're using a parabolic dish to hack into a network endpoint, what are we observing with that radar? Well, we can observe the range, the size of the antenna, angles, which is going to be azimuth and elevation. This is really getting your bearing, especially if it's moving and you're using multiple antennas to hack into an endpoint. So let's go through a simple example. When you're talking about GPS, you need three different architectures to be able to triangulate a signal or triangulate a particular endpoint's mobile, antenna, or to pinpoint wherever you're trying to transmit a signal that's going to affect an endpoint. And so azimuth and elevation is very important. Speed, once again, if next generation telecommunication devices or endpoints are mobile, then essentially you need to be concerned about how fast it's going to be, where it's going to be. So once again, going back to GPS, if you have a drift associated with your architecture or your antennas that you're using to hack into a system, then you have to account for the speed so that you know where your architecture is or your antennas are before you commit to a hack. Going further, you have different features that are associated with this. So this is a weird looking endpoint, or it's a weird looking setup for multiple patch antennas if you were going to do that. So if you're going to have patch antennas here communicating with different IoT devices or end user devices to do artificial intelligence at the edge. What this is saying is there are different features that are associated with the devices that you're looking at or the antennas that you're looking at. Each is going to be unique in some form or fashion, and so that's important to be aware of. So let's move forward. That gives you a real good baseline on what RCS is, what the antennas are, what we're using to hack into endpoints, and why it's important. Once again, it doesn't have to be a parabolic dish. It really could be any different type of antenna. There's multiple different kinds. We'll talk about isotrophic later on. We'll talk about different dipoles. We'll talk about Yagi antennas and a lot of fun stuff. So we're going to talk about the nuts and bolts of signals first. Just a real high baseline. And then we'll see different decibel examples to be able to calculate the EIRP of an antenna, to calculate the signal loss associated with an antenna, or the gain, or the whole suite of hacking end to end. So in this case, forgive me for my drawing. Did not go to school to be an artist. On the Y, we'll have the amplitude. And on the X, we'll have time. And this is very important. So in this scenario, it's basically a sine wave. These are supposed to be equal on each side. Obviously, they're not equal. Not the best at drawing. But let's assume that it's a standard, uniform sine wave. So it's going to start at 0. And in this case, we have the wavelength. And you can also consider this a cycle. Amplitude is how high it's going to go up. So that's the amplitude. And the frequency is calculating how many cycles you have in a given time. So frequency in this case, or freak, is going to be 1 over s, which essentially equals speed of light over wavelength. And we'll go through different examples. The main point to be concerned with here is that as the frequency increases, so frequency increases, you have a decrease in the wavelength. An increase in the wavelength will have a decrease in the frequency. So you can consider them basically two sides of the same coin. If you use one, or if you try to increase one, you're going to decrease the other. And in this case, it's important because when we talk about encoding schemes, we'll look at using particular frequencies associated with one section of the modulation scheme. And then what we can do later is associate different blocks with it and filter out phase shifts to make it more usable. When I say more usable, I mean you'll get more transmission out of it for the given bandwidth. And essentially, that's what 5G is doing. So it's taking circular quarks. Basically, just look at a tornado turned on the horizontal axis. And what they're doing is they're throwing tennis balls that are on different, aspects of the 360-degree tornado, and it's able to do different spatial streams associated with it. And we'll talk about that later, but you're not really concerned about that now. So when you're talking about looking at frequency, you really want to look at hertz, the standard unit of measure, hertz. So a hertz equals cycles per second. And so what's important here when you're looking at cycles per second, so we talked about looking at Wi-Fi within 2.4 to 5 gigahertz. We talked about 5G looking at 62 gigahertz. And essentially a gigahertz takes the base value, or the standard unit of metric, for this particular frequency band, and makes it a lot larger. So in this scenario, you have kilohertz. These are ones that you should be very familiar with. And if you're not, then you have to memorize them for your test. Kilohertz, megahertz, that's going to be 1 million. And then gigahertz. Okay, so the goal is not to, be an expert in electronic warfare. The goal is to then take the frequency bands that your device or the target's device is operating in, and essentially selectively filter the information coming out from that receiver or from that transceiver, and be able to exploit it in some form or fashion. In order to do that, in order to even get to that point, you have to be eminently familiar with the EMS or electronic magnetic spectrum to be able to pinpoint, where can we start targeting this antenna, where can we start targeting this transceiver, etc., etc. And you can look up, what common household items are running in what frequency band. So you can look up microwaves, or you can look up your television, you can look up a bunch of other things to become more familiar with, what's in the EMS and what frequency band they're operating in. So we talked about phase shifts, and this is really the extent that we're going to go today on looking at waveforms and other things like that. So once again, just assume that's a sine wave. Perfect, right? And then we have a second one. Let's say that's another sine wave. Once again, it's supposed to be a uniform sine wave, but it's shifted. So what we call that is the phase shift. So let's say it's phase shifted 90 degrees. And so what we can do is we can then determine, actually if we were going to encode this for information, the phase shift would allow us to have different data streams associated with one particular, signal message. And in this scenario, Cisco really talks about and harps on 2.4 gigahertz, and I'll give an example on this really quick. Let's assume you have 14 different bands, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14. So when you're talking about the 802.11 standard, you have different bins or channels that are associated with it. So each slot is going to be a channel. And when you have different phase shifts, you can essentially associate the particular waveform of interest. So let's say we're talking about the left or the right, associated with different channel overlaps. And what it will do, it'll allow separation between the two to essentially be able to filter out messages so you have minimal interference. Now, if you have overlapping waveforms within the same channel, then you're going to have more interference. Basically, interference is bad. The more you have, the less you're able to get from that particular data stream. And we'll talk about what that means for receiver selectivity sensitivity index, or RSSI, and essentially floor noise, and how to determine and differentiate whether your device is going to be able to pick up the different signal that's coming out and be able to separate it from the baseline to provide a better signal and noise ratio. In this scenario, Cisco recommends, and other standards and companies recommend, separating different channels. So let's say you use channel 1, use a different channel in the middle, different channel towards the end, and then you use the last channel. Essentially providing an avenue to separate your interference to maximize the signal noise ratio you have for each given bandwidth. And what is concerning here, and what should you be aware of? For each section that we're looking at, for each signal, let's say you're given just a baseline, typical, uniform signal. You could say that's the center frequency. And you could say that the total signal from start to end is going to be your bandwidth. So once again, we're minimizing interference, maximizing signal and noise ratio by separating them in different channels or channel spacings, so that we can adequately provide enough information within the bandwidth provided for each channel that the end user device or the antenna on the other side is able to get that information. And what I want to talk about next is, depending on the phase shift, also depends on whether it's constructive or destructive. And essentially, you consider two waveforms. If they're the same, then essentially it's going to be twice as large, and it's going to be constructive. If they're phase shifted completely, so they're opposite in every respect, then it's going to be destructive, and you're just going to see a straight line. The last part to touch on, but is not really concerning for hackers, it's important to be aware of that each waveform is actually composed of two parts: electric, or the electric field, and the magnetic field. Both are perpendicular to one another, so depending on the polarization of the waveform depends on whether you have a horizontal electric field or a vertical. Oh, sorry, got a little nervous. Whether you have a vertical electric field or horizontal electric field. And so that really determines what you can do with that particular waveform. That's starting to get into some really advanced mathematics and some advanced techniques that we might cover towards the end of our time making these videos, but is not as concerning. What's concerning for hackers and for Aircrack and John using that information and then pass hashes or accounts to John the Ripper is targeting specific frequencies so that you can either exploit it by sending malformed waveforms, or essentially targeting side channel attacks or side lobes. Something we're going to be talking about pretty soon. I'm excited to be able to teach everybody, and I hope you have a great day. Enjoy these videos. Subscribe, like, comment. Take care. Bye.